Hello everyone, we are from EKC354 Group 4 and I am Heah Joo Yee. The topic of our project is removal of oil droplets using Amine functionalized magnetic nanoparticles, in short ANNPS. So first, I'm going to discuss our pollutant, which is crude oil, and the nanomaterials we selected, which is Amine functionalized magnetic nanoparticles. Why do we choose crude oil instead of other pollutants? This is because water removed from the industry often contains stable oil in water emulsions that are difficult to be separated out using current technology. There are several processes commonly used in current technologies to eliminate oil from water, for example, photooxidation and microbial biodegradation, but these processes bring disadvantages to the environment and living organisms. Also, estimated crude oil sent out to the environment is around 600,000 metric tons per year, and it is toxic due to the presence of polycyclic aromatic hydrocarbon. These are several examples of the biggest oil spill cases in the world. If just consider the oil spill case within our country, the example is at Sungai Selama, and it causes water storage problems to the resident. Therefore, Amine magnetic nanoparticles are proposed to solve the oil spill problem. But why do we choose Amine magnetic nanoparticles? This is due to several reasons. First, Amine magnetic nanoparticles have large surface area to volume ratio as common nanoparticles characteristic, which can provide a larger area for them to interact with the pollutants, so can remove the pollutant effectively. Second, Amine magnetic nanoparticles are recyclable and reusable, which up to 6 cycles with efficiencies greater than 96%. Therefore, by using Amine magnetic nanoparticles, less time is needed to produce it again for every cycle. Next, Amine magnetic nanoparticles are environmentally friendly, as they do not form any toxic byproducts after the reaction. Last but not least, Amine magnetic nanoparticles can be synthesized by cold precipitation method under alkaline condition, which is not difficult to be synthesized in laboratory.
Hello, I'm Qian Hui, and in these two slides, I shall explain the interaction between ANNPs with crude oil droplets of different acidities. The graphs in this section are the graphs of interaction between the ANNPs. Based on the graphs obtained, the interaction between ANNPs and both TAN 2.9 and TAN 4.9 crude oil droplets are similar. The net DLVO interaction energy for both cases are attractive. Most of the times, the van der Waals interaction is greater than the electrostatic double layer interaction, except for certain range of separation distances. 1.9 to 2.9 nanometers for TAN 2.9 and 0.8 to 3.5 nanometers for TAN 4.9 oil. Besides that, TAN 4.9 crude oil is more acidic and has more carboxylic acid groups than TAN 2.9, thus resulting in a more negative surface potential and a greater electrostatic double layer interaction with ANNPs. The net DLVO interaction between the ANNPs is repulsive for separation distances less than 1.7 nanometers because repulsive electrostatic double layer interaction dominates within the range. Van der Waals interaction is greater than the electrostatic double layer repulsion beyond 1.7 nanometers, hence resulting in a net attractive DLVO interaction in this region. The overlapping of electrostatic double layers from both positively charged ANNPs causes them to repel each other. Due to the net repulsive DLVO interaction, when the separation distance is less than 1.7 nanometers, the ANNPs are considered to be colloidally stable. This slide shows the graphs of interaction between ANNPs and water molecules in brine. The net DLVO interaction between ANNPs and water molecules in brine is attractive, with the electrostatic double layer interaction dominating over the van der Waals interaction until the maximum separation distance calculated, which is 100 nanometers. However, the interaction energy is significantly less than the interaction between ANPs and crude oil, which is the pollutant. Hence, more AMPs will be attracted to the crude oil droplets than water molecules.
It's me, Joo Yee again. I'm going to talk a little bit about separation kinetics. The graph at left-hand side is picked out from the article we found, which is the relationship between total separation time and oil magnetic nanoparticle aggregate diameter. After plotting the same graph in Excel, the graph gives the fifth order polynomial. The fastest total separation time is 5 minutes, which is the size of oil magnetic nanoparticle aggregate reaches the diameter of 316 nanometer. And from the graph, it shows that the total separation time decreases as the oil magnetic nanoparticle aggregate diameter increases. This is because the oil magnetic nanoparticle aggregate becomes larger as the mixing time for demulsification of oil by amide magnetic nanoparticles increases. When mixing time increases, the collision probability between amide magnetic nanoparticles and also between amide magnetic nanoparticles and oil magnetic nanoparticles increases as well. Thus, the time for complete magnetic separation will decrease.
Greetings, I'm Chong I shall elaborate regarding the spatial resolution through a case study and industrial application. To find out how the AMPs will perform in real-life conditions, the Deepwater Horizon oil spill was used as a case study. The Deepwater Horizon oil spill incident in 2010, which is the biggest oil spill recorded in history, is taken as a case study. Approximately 492 million liters of oil was spilled. An estimated amount of 8.61 times 10 to the power 5 kilograms of AMPs would be required to clean up, which occupies approximately 166.57 cubic meters of space. The magnet used would be N50 magnets arranged in a Hilbert array. The minimum expected efficiency is 95%, with 2.46 times 10 to the power of 7 liters of oil remaining after removal. And the maximum expected efficiency is 99.9%, with 0.05 times 10 to the power of 7 liters of oil remaining after cleaning. The AMPs can be recycled for at least 6 times. From this case study, we can conclude that the magnetic oil spill removal technology has not yet reached the stage of development to clean up large-scale oil spills, and may be more suitable for smaller-scale oil spills. We hope that further research can be conducted to make cleaning of large-scale oil spills a practical industrial application. To practically implement AMPs for oil spill absorption in real world, the process and equipment used by CleanMag technology, which also uses magnetic separation to clean up oil spills, may be referred. CleanMag is a developed and patented oleophilic, porous, magnetic and oil-absorbing material. It absorbs only oil and no water. It has been tested and demonstrated on a large scale and in real conditions and has performed successfully. The CleanMag is dispersed in granular form over the area of oil spill on the seawater. The spilled oil is instantaneously absorbed into the material pores by capillary action. It is unsinkable even under harsh weather conditions, limiting the oil spill expansion through emulsification. After the oil absorption, CleanMag can be collected from the sea immediately by using vessels equipped with magnetic means of collection, such as the magnetic drum conveyor belt system. CleanMag is then transferred to non-magnetic drums. Both CleanMag and oil adsorb can be separated to be reused later. The most effective method for oil extraction from CleanMag is through compression to drain the oil. On the other hand, AMPs may also have the same disadvantage as CleanMag, in which there is a need of a certain barrier to be set up around the oil spill area on the sea to ensure all the oil MMPs complexes are recovered to virtual 100%. Let's move on to the limitation of the application of AMPs for oil spill removal from the seawater. Firstly, the manufacturing challenge to manufacture stable, high-quality and low-cost AMPs faster through a simple method. Besides, although the regeneration method of AMPs can be improved through the improvement made in thermal sensitivity or pH sensitivity of the AMP, discharge cannot be done according to the characteristic of specific oil in the wastewater. Further, extensive research should be done on the toxicity of the AMPs on the environment, as it may be left behind on the sea after the recovery process. Actual magnetic strength required to completely recover the oil MNP complexes in the actual sea conditions should also be determined. The same goes to the actual amount of AMPs required. The amine and supporting materials in the AMPs is important to prevent aggregation of the MMPs and prevent the toxicity from leaking out. Therefore, the respective stability should be enhanced.